Welcome, dear students. I am going to continue the energy storage part of Module 3 with the concept of ultra capacitors or supercapacitors. The frequent start-stop operation of EVs adversely affects the life cycle of batteries due to the high variation of the battery discharge profile. Typically, the EV batteries they have high specific energy. The term specific energy has already been explained. That is suitable for a reasonable driving range and cruising at a reasonable speed. However, they have significant difficulty providing certain bursts of power for rapid acceleration and hill climbing due to their low specific power density. It may be noted that the high peak power demand deteriorates the life of the battery, and the low specific power density of the battery jeopardizes the regenerative braking system because the battery cannot efficiently absorb the regenerative energy. One way to uh, overcome this issue is to increase the capacity of the battery, but the overall cost of the vehicle performance will deteriorate. Now, there comes the solution in the form of ultra capacitors. Ultra capacitors are energy storage devices with high specific power density, high efficiency, and long cycle life with the disadvantage of having only low specific energy density. They can provide the high output power within a short time, thereby making them suitable for high power demand conditions. Furthermore, what happens, their high specific power density makes them an excellent candidate for braking energy recovery. It is possible to take the advantage of both the ultra capacitors' high specific power density and the battery's high energy storage capability by using a combination of battery and ultra capacitor. This combination is actually known as the hybridization of energy sources. However, the integration of ultra capacitors and batteries requires additional power electronics, thus resulting in increase in the initial vehicle cost. Now, the basic principle of ultra capacitors. So, this is the basic principle of a typical electric double layer capacitor. The double layer capacitor technology is the major approach to achieving the ultra capacitor concept. The basic principle of a double layer capacitor is illustrated um, when two carbon rods are immersed into a thin sulfuric acid solution separated from each other, and we apply the voltage with increasing voltage from 0 to 1.5 volts, almost nothing happens up to the voltage of 1 volt. Then at a voltage of little over 1.2 volt, a small bubble appears on the surface of both the electrodes. The bubbles at a voltage above 1 volt integrates the uh, electrical decomposition of water. Below the decomposition voltage, while the current does not flow, electric double layer occurs at the boundary of the electrode and the electrolyte. The electrons are charged across the double layer and for a capacitor. So this is the collector, the polarizing electrodes, the charger, the electrolyte, and these are the electrical double layers: positive, negative, positive, negative. An electrical double layer works as an insulator only below the decomposing voltage. The stored energy expressed as half CV square, where C is the capacitance, V is the usable voltage. Up to now, a capacitor's rated voltage with aqueous electrolyte has been about 0.9 volts per cell, and with non-aqueous electrolyte, it is about 2.3 to 3.4 volts for each cell. Now, coming to the next candidate, that is the fuel cell technologies. The powertrain of a fuel cell electric vehicle is analogous to that of a battery electric vehicle with the exception of an added fuel cell stack. All fuel cells are comprised of anode, cathode, and an electrolyte that permits the charges to pass between the two charge sides of the cell, and as electrons are attracted to the anode from the cathode, they produce direct electric current. And we have the fuel in the form of hydrogen and the oxidant in the form of oxygen. Each individual cells produces very little electricity, but if they are stacked in series and parallel, they can maximize the amount of voltage and the output current. The majority of fuel cells are powered by hydrogen, and this process operates by directly feeding hydrogen to the fuel cell system or by reforming hydrogen rich fuels such as methanol, ethanol, or hydrocarbons. There are different types of fuel cells that are available in the market, or some are under development, and there are different ways of classifying fuel cells, such as the type of chemical reactions that takes place, the type of catalyst used, the type of fuels, the operating temperature. But the typical classification includes polymer electrolyte membrane fuel cell, direct methanol fuel cell, alkaline fuel cell, phosphoric acid fuel cell, molten carbonate fuel cell, and solid oxide fuel cells.